Welcome to Online Algebra 2. This section is 6.8, Graphing Radical Functions. So our objective here is to graph the square root functions and other radical functions, mostly just cube root. We'll stay away from anything too crazy here, and we'll focus just on the square roots and the cube roots. And what you really need to understand is the square root function is the inverse of a quadratic function. Okay, so when we take the inverse of a function, right, we flip it over the line y is equal to x. But we're also going to have to restrict the domain so that we actually get a function. Okay, so if we see a parabola here, we can see that we can draw a horizontal line that crosses the graph in two places. So that means if we were to flip this function across the line y is equal to x, it would now not be a function anymore because it would fail the vertical line test. So basically, if we look at the original function and we fail the horizontal line test, the inverse will fail the vertical line test. And that's a way that we tell if something is going to have an inverse that is a function. Okay, and that's pretty much what this says up here. So vertical line can intercept the graph of f inverse in 2 points, and that means f inverse is not a function because it fails the vertical line test. But if we restrict the domain of f so that the inverse of the restricted function is a function, then we can have these two things work nicely together. So basically, if we take the parabola and we say that x has to be greater than 0, now when I flip it over, I do get a nice function that starts at 0 and continues up and to the right indefinitely. Okay. And this makes sense to have this function, the radical function, not exist for negative numbers, because we should know that we cannot do that, right? The square root of -1 gives us I, which we can't graph on a real number line. So that means that having this point down here wouldn't actually make sense because it's not an output of the radical function. Okay? So for these two things to actually work together to be inverses of each other, you do have to restrict the domain of the quadratic function. All right, so that means that inverses of power functions with domains restricted, mostly for even powers and not for odd, form radical parent functions for families of radical functions. So in particular, f of x of the square root of x is the parent function for the family of all square root functions. And just like every other family of functions, we can apply the same transformations that we would in the past for functions that take on this form. So that means that if our parent function looks like this, if we put a negative in the front, it's a reflection across the x-axis. If we put a number in the front, it would stretch the function if it's bigger than 1, compress the function vertically if it's between 0 and 1, and if we put a number in there, it would move it left or right, a number out there, up or down. Left for a negative, right for a positive, up for a positive, down for a negative. And this applies to any other radical functions. But again, we're probably just going to look at square roots and cube roots in this section. So let's take a look at first the parent function. And then we'll look at this function, the square root of x minus 2. And then we'll look at the square root of x plus 1. All right, so parent function. You're not sure what the function looks like? Make a table. And again, we cannot plug -1 into this function because this gives us something that is undefined. So the only number that we can start with here is 0. And if we take the square root of 0, we get 0. Okay. Now, the trick to graphing square root functions is to pick numbers that work well with whatever square root you're dealing with. In this case, since we just have the square root of x, pick numbers to plug in that are perfect squares, like 1, like 4, like 9, 16, and, well, this goes up to, and let's try 25, okay, because it goes all the way to 25 here. Okay, so those are perfect squares. So the square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, and 5. So if I graph this, I get 1, 1, 4, 2, that's 5, 4, 2, 9, 3, 16, 4, and 25, 5 to give me a curve that looks like that. Okay, again, the trick is to use numbers that work with the root. Okay, let's go to red and graph the square root of x minus 2. Well, you could plug all sorts of numbers in, or you could just find the starting point and then use the pattern of the parent function that you go right 1 up 1, right 4 up 2, right 9 up 3, right 16 up 4, right? Perfect squares, just like we did with square root with parabolas. Only this time we don't even have to reflect anything. We just have to do it once. Okay, so if I know the starting point, if I know where the function begins, then I can make the rest of it with the rest of the transformations. And I know if I plug in 0, I would get -2. So from that starting point, if I go right 1, the square root of 1 is 1. From the starting point, if I go right 4, the square root is 2. If I go right 9, it's 3. 16 is 4. And 25 is 5. And you can see that this function, that every single point on this function is simply moved down 2. Now, could I pick some of these other numbers in between? Could I graph an input of 5? Sure, I would just need a calculator to take the square root of 5 to get 2 point something, 2.1-ish, yeah, 2.23. So I could graph those, but why would you want to? Right? Why would you want to graph 2.23 as opposed to just graphing 2 and then just graphing 3 for an input of 4 and an input of 9? All right, let's do the blue one. Exactly like the black one, except now instead of shifting the function down 2, we just shift all the points up 1. So from the starting point, if I know the starting point is +1, I go right 1 up 1, right 4 up 2, right 9 up 3, 16 4, and 25 5. And we have our similar function to the rest. Right? No stretches, no compressions, nothing weird. Okay? Just shifted up 1. Let's try one more of those with our got it problem. 2 more. Okay? So very similar here. We'll start with this one, x plus 2. The function starts at 2. And we just go right 1 up 1. 1, 2, 3, 4, 1, 2. Square root of 4 is 2. And look what happens. If I plug in 4, I get 2 plus 2 is 4. So the point is 4, 4. So you could do that. You can make a table, right? I'm just saying this is a little bit faster. So from here, we go right 9 up 1, 2, 3. We go right 16 up 1, 2, 3, 4. And 25 and 1, 2, 3, 4, 5. And there is my function, right? It starts, goes forever to the right. It starts at 0, 2. This one, let's do this one in red. This one starts at 0, -3. Starts down 3. There's my next point. My next point, right 4 up 2, right 9 up 1, 2, 3, right 16 up 1, 2, 3, 4, right 25 up 1, 2, 3, 4, 5. Exactly the opposite of the technique that we used to graph x squared. Okay, now watch what happens here. Now this function is moved left 4. So there's my starting point. It's not called a vertex, really. It's just the place where the function starts, the place where the square root starts. Okay? And there's the next point. Right 1, up 1. Right 1, 2, 3, 4, up 1, 2, 3, 4. Oh, sorry, up 2. Okay? Plug it in. Plug in 0. What do you get? 0 plus 4 is 4. Square root is 2. Plug in things that make this square root work. So don't plug in 9, plug in 5, right? So here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 away from the starting point is actually the coordinate 5, and the output would give you 3. Okay, so plug in numbers that make the square root a perfect square. In the previous problem, I could just plug in perfect squares. Here, I have to plug in perfect squares minus 4, like 12. 1, 2, 3, 4, and 21. 1, 2, 3, 4, 5. Right, 21 plus 4 is 25. Square root of 25 is 5. So here is my curve, and I could have counted from the starting point to get those numbers, or I could just take perfect squares and subtract off the 4 because I'm adding 4 and I want the answer to be a perfect square. For this one, y minus 1, let's do that one in red. So now my starting point is 1 to the right. Again, my next point would be right 1 from the starting point, up 1. Right 1, 2, 3, 4, up 2. Right 1, 2, 3, 4, 5, 6, 7, 8, 9, up 3. Okay, so now we're not shifting right down, we're shifting every point to the right of the parent function 1. Remember, the parent function starts at 0. Okay, so again, don't plug in perfect squares. Plug in perfect squares. Plug in one bigger than a perfect square. This number minus 1 should be a perfect square. So like 17 would give me 4. Like 26 would give me 5. Off the graph a little bit, but it's okay. You see these are getting a little bit closer together because we're not shifting it down, right? We're shifting the whole function to the right or left. Let's try it again. Same idea here, right? Minus 3, we're going to start there. There's my second point. Always try to fill the graph, no matter what graph you're dealing with here. So we want something minus 3 as a perfect square. So that's going to be 1. And then 6. 6 minus 3. No, sorry. 1, 2. Right one up one. 1, 2, 3, 4. Up 2, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that was right. Yep, because I shifted it the wrong way. X minus 3 shifts to the right 3. Okay, sorry about that. Right 3. Right one up 1. 1, 2, 3, 4. 1, 2. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 12 minus 3 is 9, which gives me uh, the square root of 9 is 3. Makes more sense here. I'm only going to be able to fit 16, 17, 18, 19, and up 4, and 20, 28 is a little bit off the graph, so we'll leave that. Here's my graph. Let's do y plus 2. Now I'm going left 2. Okay. 1, 1, 2, 3, 4, up 2. And things that are 2 below a perfect square. So the next one is 9. Right, so 7. 7 plus 2 is 9, which makes my graph kind of look like that. And you can see that it's getting really uh, really close to this other line here, which is okay, right? It's just gonna, they're both gonna flatten out eventually. And this left one is just gonna go up a little bit faster. So the next one would be this one, right? No, 14 would be 4, and 23 would be 5. So we're gonna get close to that line, but not quite cross it. Okay, so those were shifts left and right, and or up and down first, and then left and right. Okay, so in 2.27, we knew that any transformation of some sort of parent function, right, whatever this function happened to be, this number in the front here indicated a vertical stretch or compression. So similarly, for the square root function, it's going to be a vertical stretch if it's bigger than 1, and a shrink, a compression, if it is less than 1. Negative numbers reflect in the x-axis. They have nothing to do with stretches or compressions. So this one's kind of going to be a pain. Okay? The trick is to find out where it starts. It's going to start right 3, 1, 2, 3, up 1. It's going to start there. Okay? Now, don't worry about anything else. We're going to make a table for this. We're not going to try to do all the transformations in our head like we did last time in the last problems. Okay, we're going to make a table for this. The trick to making a table is plugging in numbers that will give you perfect squares underneath the radical. Okay, so 1 to the right of the radical. So I'm going to plug in 4. 4 to the right of the 1 to the right of the starting point. 1, 2, 3, 4. So I'm going to plug in 7. Okay. Then I'm going to plug in 12. Right? Because 12 minus 3 is 9. 7 minus 3 is 4. 4 minus 3 is 1. They're giving me perfect squares. Let's try one more. So the next one would be, next perfect square one is 16. So I want to plug in 19. All right, so let's plug in 4. 4 minus 3 is 1 times negative 1/2. So that's negative 1/2 plus 1 on the outside to give me positive 1/2. So the next point would be 4 and 1/2 right there. Well, that's weird. It's going down instead of up. And it should, because the negative reflects it in the x-axis. Let's plug in 7. 7 minus 3 gives me 4. Square root of 4 is 2. 2 times negative 1/2 is negative 1, plus the 1 on the outside gives me 0. So 7 gives me 0. All right, 12. 12 minus 3 is 9. Square root, right, 12 is going here. 12 minus 3 is 9. Square root of 9 is 3. So that's negative 3 over 2 plus 1 gives me negative 1/2. So 12 gives me negative 1/2. You see I'm kind of going down by halves here. So you can sort of get this pattern here. Let's just plug in 19. We should get a negative 1. Let's check. 19 minus 3 is 16. That's 4. That's negative 2 plus 1. That's negative 1. So there's my pattern. Right. On the last pattern, on the last graphs, everything was going up by 1. These ones are going to go lower by 1/2. So we get my graph that looks kind of like that. Oof. So, and it doesn't hook back up at the end. Sorry about that. Right. It just keeps going in a nice smooth curve. If you have to get a good picture of this, put it on desktops there. Okay. So notice the pattern here, right? We're still going a perfect square to the right of the of the starting point, and then we're taking the number that is in the front, the stretch or compression, and since all the other functions went up by, we're going up one each perfect square, this one is going to be going down 1/2. So if we were to look at this problem, I would expect each one to go up 3. Let's check it. So my starting point is left 2, down 4, 1, 2, 3, 4. So there's my starting point. If I were to make a table, I would go right 1. So I want -1. I would go right 1, 2, 3, 4. And so I would want 2. And watch what happens here. If I plug in -1 plus 2, that's 1, times 3 is 3, minus 4 is -1. So look at that. I went right 1. Instead of going up 1, I would go up 3. And then in my next point, 2, which would be right 1, 2, 3, 4, instead of going up 2, I would go up 1, 2, 3, 4, 5, 6. 2 times the 3. Remember when we graphed 2x squared with this method, right? We used the points of the parent function and we multiplied all the outputs by 2. So again, this was -1, or let's just look at the parent function, right? So we'd go 0, 0, 1, 1, 4, 2, 9, 3. Okay, so these points to the right of the starting point still hold. These outputs are just going to get multiplied by 3. So the next one, I'm going to go 9 to the right of the starting point, and I'm going to go up 9. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there I'm getting my graph going sort of like this. The next point that I want to plug in is the next thing that's going to make this thing a perfect square. So that was 1, 2, 3. So it's going to be, I want the underneath to be 16. So I'm going to plug in a 14. So that's be 4 times 3 is, well, I could just look at 14. I know I'm going to go 3 above this one. 1, 2, 3. I'm going to go right there. Let's double check. 14 plus 2 is 16. Square root of that is 4 times 3 is 12. Minus 4 is 8. And we have 14 comma 8. Let's see if 20, yeah, 22, well, 1, 2, 3, just barely. Okay, 22 just fits. 3 above my last point. And you can see I thought it was going to go off, but it didn't quite because it flattens off as you get steeper and steeper. Okay, so now instead of these jumps being 1 higher each perfect square, they're actually going to be 3 higher each perfect square. And again, if you don't like this method, the other method to use is make a table, but make your inputs work with the radical in your table. All right. This is just a graphing problem, so I'm going to just skip over this real quickly. You can try this on your own if you want to. The answer is going to be C. We can solve it. We could try to solve it algebraically, but you know this is going to be a graphing problem, modeling problem. So the one thing I'll mention is that with the cube root right there, if your graphing calculator doesn't let you do that, you could always change this to x minus 1950 to the 1/3 power. It means the same thing as cube root. Right, and we could actually solve this. This is not terrible, right? Just divide out the 75,000. So 250,000 divided by 75,000 gives me 3.3. And then we just raise everything to the 3rd power. and we get 37-ish is equal to x minus 1950. And then I just add 1950 to both sides to get 1987.04, but close enough. And it says about. Okay, so we could solve this algebraically. You could plug this into a graphing calculator and graph it, whatever makes you happy. Okay, so we looked at square roots. Let's look at the parent function for the cube root. Now, unlike this, the square root of -1 is undefined, but the cube root of -1 is -1. So the biggest difference between cube roots and square roots is that cube roots, the domain is all real numbers, right? And when the patterns for graphing square root functions also apply to these radical functions, right? All the shifts and all the things that we're going to do are the same. The trick to graphing a cube root is use numbers that are perfect cubes. What numbers are perfect cubes? 1, 8, 27, 64. Okay, so really we're not going to get much here because most of my graphs that we're going to draw are not really going to be, 64 lines big, right? We're just going to 1 and 8 is usually good enough. Okay, so let's pick numbers that work well with the cube root. Start at the beginning. Start at the inflection point, right? It's not the beginning anymore. It's kind of this little turning point. That is going to be the middle of the function. That is what we're going to shift around. So we're going to shift it left 1 and down 4. So that's where my middle of the function is. So now when I make my table, right, use numbers that are a perfect cube away from the starting point. So we start there and we go right 1. So let's plug in 0. Let's go right 8. So let's plug in 7. And that's about it. We're not going to get 27. Okay. But then we're also going to have to plug in left 1 and left 8. Right? Because this function has 2 sides. But we can do something really cool if we just get these 2 right here. So let's plug in 0. 0 plus 1 is 1. Cube root of 1 is 1. Times 2 is 2. Minus 4 is -2. So we get -2. 7, that's 8. So cube root of 8 is 2 times 4 is 4. So that's 0. So 8, 0. Now, cubic functions are always odd. So that means they're going to be reflected across the parent function. Is going to be reflected across the origin, and it's going to be an odd function. This function is going to be reflected across this point. So it means if I went right 1 up 2, I'm going to go left 1 down 2. This one is not going to be over here, right? From this point, if I went right 8 up 1, 2, 3, 4. I'm going to go left 8, 1, 2, 3, 4, 5, 6, 7, 8, down 1, 2, 3, 4. Right? And there's my graph. So it's not going to be too bad. Right? We get the idea there. Okay? So again, the trick to this is use numbers that you can plug in nicely to the cube root. Okay? Last thing here is that we can graph cubic functions if they look like this using transformations. If you want to do that, you have to get the radicand to have a coefficient of 1. Okay. So if you can do that, if you can make the radicand have a coefficient of 1, then it's going to be much easier to look for the transformations. So if we're looking at a function like this, here's what we want to do. We want to make this have a coefficient of 1 in front of it. So what we do is we factor out the 9, which gives me x plus 2. Now, I can take the square root of that 9 and bring it to the outside. That is much better. That tells me now that my square root function is stretched by a factor of 3, and it is moved 2 units to the left. And I wouldn't have got that so much from looking at it this way. Okay, so factor out a common factor and make it so that there's a 1 in the front of the variable. Okay, let's try one more of those. Factor out the 8. Okay, and then the cube root of 8 is 2. So now this is the cubic function stretched by a factor of 2, shifted left 4 and down 2. Okay? So in this function, in this chapter, right, there's all about graphing. Right? This is graphing by hand. So when you're doing this work online, I highly suggest using a graphing calculator to help check your work. Okay, so if you need to graph any of these functions by hand, you could use all these techniques, but in the end, we can probably just use a graphing calculator to help us out with most of these. But you should understand just by looking at the function that this one is shifted to the left and reflected. This is reflected and shifted up 5. And you can factor out the 8 and the 4 in both of those to describe the transformations that way. So that was 6-8, graphing radical functions.